Hello, welcome to our last set of notes for mathematical reasoning. This is our last section to cover before the last exam. There's no cumulative exam for this class. That would be kind of a crazy thing, so don't worry about trying to study for some kind of cumulative exam. The last exam will just cover the math and the arts, so the math and the visual arts, math and music, math and poetry, which is our last session, which we're going to cover today. So we're going to talk about how math intersects with poetry. So there have been connections between poetry and math dating back to antiquity. Some of these poems we're going to cover are from thousands of years ago, and it's still happening today. There are people making modern music and poetry based on mathematics right now. So we're going to cover three main different ways that the connection occurs between math and poetry. And the first are literally just poems about math. There are poems that are written presenting a math problem for someone to solve. They are about mathematics. That's what they are. So the first one we're going to talk about is Archimedes' cattle problem. So 250 BCE, Archimedes presented this problem as an epigram, a form of poem. And in this epigram, he basically lays down the things you need to know so that you can figure out how many cattle the sun god Helios has on the island of Sicily. So in Greek mythology, this sun god Helios has this big herd of cattle. If you ever read or studied or learned about the Odyssey, with Odysseus trying to get back after the Trojan War, most of his sailors are killed because they actually try and take some of the sun god's cattle, and so that's why they end up dead. So they shouldn't have messed with Helios. But this poem, Archimedes is going to present this big problem, and we're going to try and solve and figure out how many cattle the sun got. So it starts off. If thou art diligent and wise, O stranger, compute the number of cattle of the sun, who once upon a time grazed on the fields of the Thrinacian, meaning three-cornered, isle of Sicily, divided into 4 herds of different colors, one milk white, another glossy black, a third yellow, and the last dappled. So we have white, black, yellow, and dappled. I think it means like spotted. So those are the 4 main herds we have. Those are the 4 colors: white, black, dappled, yellow. So we're going to use those when we're trying to figure this out. Instead of trying to figure it all at once, we'll find the different herd sizes, and then we'll get the total later. Okay. In each herd were bulls. So he's going to number out the bulls and kind of help us figure out how many bulls there are. Mighty in number according to these proportions. Understand, stranger, that the white bulls were equal to a half and a third of the black together with the whole of the yellow. So this is the first equation you give us. This is the white bulls. You can calculate if you know a half plus a third of the black bulls. So take the black bulls, a half of those plus a third of those, that number, plus all of the yellow. That's how many white bulls there are. So that was his first relation right there. So white bulls equal to half and a third of black bulls with the yellow. The black were equal to the 4th part of the dappled and a 5th, together with, once more, the whole of the yellow. So the black bulls are 4th plus a 5th of the dappled plus the yellow. Observe further that the remaining bulls, the dappled, were equal to a 6th part of the white and a 7th, together with all of the yellow again. So the dappled were a 6th plus a 7th of the white plus all the yellow. That's the number of dappled bulls. These were the proportions of the cows. So now we're looking at the cows instead of the bulls, the female cows. The white were precisely equal to the 3rd part. So the white were equal to the 3rd part and the 4th of the whole herd of the black. So the white were a 3rd plus a 4th of all the black cows. We're going to use capital letter B for black bulls and then lowercase b for black cows, so male and female. While the black were equal to the 4th part, once more, of the dappled, and with it a 5th part, and when all, including the bulls, went to pasture together. So the black were a 4th plus 5th of all the dappled bulls and cows. Now the dappled in 4 parts were equal in number to a 5th part and a 6th part of the yellow herd. So the dappled were the 5th and a 6th of the yellow. So the dappled were a 5th plus a 6th of the yellow herd. Finally, the yellow were in number equal to a 6th part and a 7th part of the white herd. So the yellow were equal to a 6th part and a 7th part of the white herd. Yellow, 6 plus the seventh of all the white. If thou canst accurately tell, O stranger, the number of cattle of the sun, giving separately the number of well-fed bulls, and again the number of females according to each color, thou wouldst not be called unskilled or ignorant of numbers, but not yet shalt thou be numbered among the wise. So he gave us a bunch of equations, basically. He gave us a bunch of relationships, kind of talked about the different sizes of the different herds, the bulls and the cows. And then he basically calls us out and says, if you can do this, then you won't be dumb. You're not unskilled, you're not ignorant, but you're not quite wise. So he's actually going to give us more later because he's not done challenging us. But even just this first one, this is kind of crazy. You notice here we have 7 different equations. We actually have 8 variables if you include the 4 different values for the bulls, the 4 different values for the cows. He didn't give us a relationship for the yellow bulls. He just gave us the relationships for the white, the black, and dappled bulls using the yellow bulls. But that's the equation. So what's the solution? How do you solve this? Well, it's actually what's considered a system of equations. We had 7 equations, but we actually had 8 variables. And as a rule, if you have a system of equations where you have multiple variables and you're trying to solve for all these different variables, you actually have to have at least as many equations as you do variables. So 7 equations actually is not enough to give a specific, unique solution. So there's not actually just one answer. There's actually infinitely many possible solutions. You can get lots of different answers for this. So what we're going to do is we're going to try and find just the smallest whole number solution. If you have whole numbers of cows, because you don't have fraction cows, that'd just be silly. What's the smallest? Well, it was solved to be the fact that the smallest number would be about 7.4 million black bulls, 10.3 million white bulls, 7.3 million dappled bulls, 4.1 million yellow bulls, 4.8 million black cows, 7.2 million white cows, 3.5 million dappled cows, and 5.4 million yellow cows. And total, that would give us 50 million cattle. That is the smallest number that solves this. So according to this, that herd of cattle, the sun god Helios, is over 50 million cattle. And you could get bigger answers. So 50 million is like the smallest possible solution. That's the smallest, these are the smallest numbers that would make all these equations true. But there's actually infinitely many bigger numbers that would also make these work. This is just the smallest. Kind of crazy. But like I said, he wasn't done. But wait, there's actually more. He actually had more constraints. That first part, that just showed that you're not, not dumb. You're not unskilled. You're not wise yet. So you have to finish this last part. So, but come, understand all these conditions regarding the cow of the sun. When the white bulls mingled their number with the black, they stood firm, equal in depth and breadth, and the plains of Thrinacia, stretching far in all ways, were filled with their multitude. So here he mentions that they're equal in depth and breadth. So if you think about that, that means that you have a line this way and this way making the same distance, which of course makes a square. So this is what we call a square number, where you have a number that's equal on both sides, a number times itself. So he's saying here that the white bulls with the black has to be a square number. So that's actually the rule requirement he's saying here. So square numbers are like 4 because it's 2 times 2, or 9 because it's 3 times 3. So he's saying that the number of white bulls plus black bulls, that value added together, has to be some kind of square number, something times itself. He's not done there, there's more. Again, when the yellow and the dappled bulls were gathered into one herd, they stood in such a manner that their number, beginning from 1, grew slowly greater till it completed the triangular figure. So now he's looking at the yellow and dappled bulls put together, and it's going to make a triangular figure. So that means you get kind of a number that's going to be a triangle. Well, triangular numbers, what you do is you start off with 1 in the corner, and the next row you have 2 because you add 1, and the next row you're going to have 3. And so triangle numbers, what you do is you end up adding just subsequent whole numbers, so like 1 plus 2 plus 3, or 1 plus 2 plus 3 plus 4, or 1 plus 2 plus 3 plus 4 plus 5. Those would be triangular numbers. So triangular numbers are the sum of all whole numbers less than or equal to the number. So the fifth triangular number is, adding up 1, 2, 3, 4, 5. Add up all those. So he's saying the dappled plus yellow has to be one of these triangular numbers. The Greeks really love their shapes. So we're not too surprised they were kind of working on shape ideas. This is pretty common for them. So he's saying that dappled plus yellow has to be a triangular number. Okay, there be no bulls or other colors in their midst, nor none of them lacking. If thou art able, O stranger, to find out all these things, and gather them together in your mind, giving all the relations, thou shalt depart crowned with glory, and knowing that thou hast been a judge perfect in the species of wisdom. So that's a little mic drop at the end there, saying, now if you can solve it, now that I gave you this last little bit, now if you can find the answer, then you can be wise. You can be like, okay, I'm really smart. Okay, so let's talk about this solution. So actually was partially solved, not extensively the whole thing, but partially solved in 1880 by A. Ampere. What he basically did is he showed that the number of cattle in the herd was a number with 206,000 digits. So he didn't, write that out because that's a long number, right? 206,000 digits. But he did show that that's how big it would have to be. It'd have to be at least 206,000 digits long. And in 1965, with the advent of computers, we were actually able to solve this and get an explicit answer. Back then, of course, computers weren't quite as fast as they are today, but even with the big mainframe computers they had back then, they were able to solve it, but it took 7 hours of computing time to just calculate the value, to get the exact value. I think later they actually published the number, someone did, in a book, and I think it was like 47 pages long. And that's just the one number that's the answer to this problem. So they probably had like a page, like here's the posed problem, and and maybe a page about how did they solved it, and then the rest of it is like 47 pages of just the number that's the answer. So it's a huge, huge number. Makes you wonder, was Mr. Archimedes just throwing together some silly relations and saying, yeah, there's an answer, without actually checking it, or was he doing something wrong? I don't know. I look at these relations to see how like 1/2, 1/3, 1/4, 1/5, 1/6, 1/7, and there's more of a pattern here. So I almost wonder if he was just kind of creating a fun and interesting pattern and not really worrying about what the actual value is. Or maybe he knew the answer. Maybe he knew this 206,000 digit number, but I kind of doubt it. But yeah, so it is a math problem. That's what he did. He posed a math problem, said, here, solve this. It was kind of an impossible problem at the time. We had to wait till we had computers to really get the answer. But that's what it was. It was a math problem. Let's look at some more. This one's a little more recent, not quite so difficult. It's a poem by Smart. It's called Smart by Shel Silverstein from 1974. It goes, my dad gave me $1 bill because I'm his smartest son and swapped it for 2 shiny quarters. Because 2 is more than 1. And then I took the quarters and traded them to Lou for 3 dimes. I guess he didn't know that 3 is more than 2. Just then along came Old Blind Bates, and just 'cause he can't see, he gave me 4 nickels for my 3 dimes, and 4 is more than 3. And then I took the nickels to Hiram Coombs down at the seed feed store, and the fool gave me 5 pennies for them, and 5 is more than 4. And then I went and showed my dad, and he got red in the cheeks and closed his eyes and shook his head, too proud of me to speak. So you'll notice here, he starts off with a whole dollar bill, right? He ends up at the end, he's got 5 pennies. Yeah, 5 is definitely more than 1, but we all know that 5 pennies is not as good as a whole dollar bill, right? That's 100 pennies. So not some great math trades here. He was kind of losing money on each trade. You can see why his dad got red in the face. But it is about math, right? The math problem of like what's greater than, which one's bigger, which one's smaller. I should mention, so on the homework for this one and the previous one, this one doesn't really have a problem to solve, but I did actually create a homework problem where you can look at percent change. Percent change is, when you look at the difference between what you have and then what you end up with, and then you turn that into a percent. So in like this question, we'd start off with a dollar bill and then you trade it for 2 quarters. You'd say, okay, well, $1 is 100 cents. You end up with 2 quarters, that's 50 cents. You subtract, you get 50 cents difference. And then you divide it by the original amount. So we take like 50 cents over the original 100 cents, and we get 50%. And that would be a 50% change because he lost 50% of his money going from a dollar bill to 2 quarters. So you'll do some percent change problems on the homework. Again, it's just subtracting to find the difference and then dividing by the original amount. I did give you a question with this Archimedes cattle problem, where basically I gave you a bunch of relations showing how if you just knew one of the numbers, I believe it's the dappled cows, I think is what the number you need to know. I'll give you that number, and then you can find the rest. Basically, I say, okay, well, you can just take these fractions times that one number, give you how big these other numbers have to be. Like I said, when we don't have all the information, we can't just solve it. Even with this extra square and triangle number, you don't actually know enough to just give one exact answer. Even this 206,000 actually is only one of many possible answers. It's just the smallest possible when you include these more relations. So for that one, I'll have you just basically multiply fractions times the given number, and you'll find the different values for the paddle sizes. All right, next one is from Bhaskara II Lilavati, around 1150 AD. I was reading about this, looking it up a little bit to kind of before I present it to you. So it's an interesting little story about this. So this is, according to legend, Bhaskara wrote this for his daughter, Lilavati. He actually wrote an entire book full of poetry based on mathematics, where they pose different problems, investigate different techniques for solving problems. I guess there was a story about maybe he saw a soothsayer, or he read the horoscope kind of thing and saw that Lilavati didn't have great outlook based on her horoscope. So he was trying to do something to help her name live in perpetuity, because he knew that her life wasn't going to be that great based on her horoscope. So kind of interesting. He's looking at horoscopes and trying to figure this out. But, okay, so this is one of the parts from that book that he wrote for his daughter Lilavati. So 10 times the square root of a flock of geese, seeing the clouds collect, flew towards Lake Manasseh. 1/8 took off for the Sathalabhadni forest. I'm sorry, I don't know exactly how to pronounce that. But unconcerned, 3 couples frolicked in the water amongst a multitude of lotus flowers. Please tell, sweet girl, how many geese were in the flock. So it actually presents a math problem asking us to solve and find out how many geese there are. So if we let x be the total number of geese, so it's like all the geese to start with. First thing it says is 10 times the square root of a flock. So we have 10 times the square root of the flock. Seeing the clouds collect, flew towards Lake Manasseh. So that's a part of it actually leaves. So the first part leaves 10 times the square root. Seeing the cloud, they fly towards the lake. 1/8 took off for the forest. So 1/8. So x over 8 would give us 1/8 of the flock. So 1/8 go to the forest. 10 times square root go, cloud watching, fly off to the lake. And then unconcerned, 3 couples, well, of course, 3 pairs of 2 is 6, so 6 geese are still left in the water. So now we know what happened. We know how many geese, we have a value for how many geese went cloud watching and went off to the lake. We have a number for the value for how many geese went to the forest. We have how many geese were left. So we can actually add these up and get the total, which we already said the total is going to be x. So we get an equation down here. Now, solving this equation is an algebra problem. I'm definitely not going to make you do. Basically, what they ended up doing here is getting everything on the same side, getting rid of the fractions by multiplying by 8. They did some squaring to get rid of the roots. So eventually end up with a quadratic equation. This is an x squared equation. And this one you can solve using the quadratic formula. And you do get 144 geese. So when they do, there's a flock of 144 geese. If you take square root of 144, you get 12. There's like 24 or 120 of them that fly off to the lake. Take 144 divided by 8. Is that? It's like, I guess I have to double check. I don't know. So 144 divided by 8 gives us 18. So about 18 of them fly to the forest, and then the last 6 are just hanging out in the water. So yeah, the solution is 144, or 12 dozen, right? That's 144. It's 12 times 12. It's 12 dozen. That's how many are left. Probably pretty intentionally. Probably started with 144 geese and then had parts of them fly off and had a certain amount left afterwards. Okay, this one I didn't throw in the homework. I'm not going to make you try and solve an algebra problem. So interesting. It is a math problem. It's a fairly complex one because it's solving quadratic equations. It's got roots and all that kind of stuff. But we're not going to worry about trying to solve it. That's beyond just scope for our class. So. Here, this one's less of solving a math problem, but about actually a famous solution, a famous math problem and the solution. So this is a limerick written by Ted Munger in 1995. It was actually part of a poetry challenge based on Fermat's last theorem, which we'll talk more about. So here's the limerick. With an integer greater than 2, it's something that one simply can't do. If this margin were fat, it'd show you all that, but it's not, so the proof is on you. Okay, so what's Fermat's last theorem and why do we have a poem about it? So mathematician Pierre de Fermat, around the 1600s, wrote down a theorem in a copy of an old Greek text called Arithmetica. So he was reading this old Greek textbook and he said something in the margin. He said, I got this theorem. And they said, well, I have a proof for this theorem. I know how to prove it, but I don't have enough room in the margin because he was just writing the edge of a textbook. He wasn't writing on a blank piece of paper. So I have discovered a proof, which is this margin is too small to contain. He never did prove it in any other location. He stated this, like, it is a fact. I know this theorem, this is true, but he never proved it. This theorem, what is this theorem? This theorem says that a to the n plus b to the n equals c to the n has no positive integer solutions for n bigger than 2. Now this might look a little familiar because if you had like a squared plus b squared equals c squared, that would be the Pythagorean theorem, and that we know have lots of nice solutions. But he said that if you make it bigger than 2, so if you do like a cubed plus b cubed equals c cubed, he said there are no nice solutions. A positive integer just means like whole numbers. So like no whole number solutions. He said you could maybe use decimals or fractions to get an answer. There's no answers with nice whole numbers. So if you have like a cubed plus b cubed equals c cubed, or a to the fourth plus b to the fourth equals c fourth, anything bigger than a squared plus b squared equals c squared, there's no nice solutions. And that's kind of a big deal to be able to say this fact. Like, there's no pair of cubes that add up and give you another cube, or no pair of fourth powers that add up to give you another fourth power. So he posed this again back in 1637. He wrote down and said, I got a solution. I don't have space to write it down, but I know this is true. So mathematicians for a long time kept looking at this and trying to figure out how do we prove this? He said he knows the proof, but we don't have his proof. We're not sure there is a proof. In fact, they called it Fermat's theorem or conjecture for a long time because they didn't have a proof for it. They just said that he did, and no one has seen it. Well, in 1993, Andrew Wiles, British mathematician, actually finally submitted a proof for Fermat's theorem. He actually worked on this proof for about 6 years. So he did this in secret, actually. So while he was working, he was a full-time professor, and he actually was kind of submitting work that he'd kind of already done, or like kind of rehashing a little bit, doing enough to keep his job and not get caught for like not doing too much work. So doing as little as he could there, but he was really primarily focused on working on this problem, trying to prove Fermat's last theorem. So he spent 6 years on it, and he finally found a proof that he was happy with, and he sent it off to reviewers, to other people. This is a big thing in mathematics. If you come up with something big, you don't just say, well, I know that's right, of course it's right. You send it off and let other mathematicians look at it, and they try and say, okay, does it make sense to me? Do I agree with you? Is your conclusion valid? And upon the peer review process, it was shown that his proof was not complete. It didn't actually quite work, which is kind of crazy. 6 years of work, and he actually had a proof that still didn't quite work. And, it's kind of a big deal he even found a proof, right? This is like a really old problem, hundreds of years old. So it was a big deal that he even got a partial proof. But what happened is it wasn't quite right. So over the next 2 years, he kept working on it, trying to see if maybe he could fix it. He was about giving up, and then he finally figured out that he had done previous work that he could use and combine with later work and figure out a proof. He actually figured a proof for this. It was kind of a different method than his original method, but it was valid. He did submit it. He got it peer reviewed. It was accepted. People said, yep, this works. This proof makes sense. There's no mistakes here. And so after 358 years, Andrew Wiles was able to finally come up with a proof for this theorem that Fermat stated back in 1637. And it was a huge deal. It was actually a really big deal. The Fields Medal is the biggest prize in mathematics. There's no Nobel Prize for mathematics, so the biggest thing you get is Field Medal, but you only get that if you're under 40. I think Andrew Wiles just missed it by a year. He was 41 when he got this proof made, so he didn't get the medal. But he did get several other prizes, one of which was a prize just for solving Fermat's theorem. He got that one. I think it ended up being about $50,000 American cash for that prize. The other prize was the Abel Prize, which I believe comes from Norway, and it was a 600,000 euros, which is actually more in dollars a prize. And this was 1995 when he finally got the final proof version. So $600,000 of 30 years ago money, even more than what we think of as 600,000 now. It's gonna buy a lot nicer house now than it would now. So yeah, huge cash prize, super famous. You know, if you talk to anybody that works in math and they knew who Andrew Wiles is because he solved this one problem. He said afterwards, like, this is probably the pinnacle of my mathematics career is solving this. In fact, that I found a proof for Ma's last theorem. So kind of crazy. So that's what he did. So, you know, again, the limerick is talking about how you can't do it with you know, power greater than 2. It doesn't work. You can't do it if the number is greater than 2. If the margin were fat, again, he had like the margin of the textbook. You know, he'd show you the proof, but it's not. So he left the proof up to us. And it took us 358 years to get it. Okay. Music and math definitely have connections as well, beyond just poetry. So Tom Lehrer is an American musician, singer-songwriter, satirist, and a mathematician. He actually wrote a lot of humorous music in the 50s and 60s, which is still around today and still fairly relevant today. He often parodied like musical styles, you know, so the old, you know, Gilbert and Sullivan musicals, stuff like that. He would kind of use that type of style for his music. He did a lot of dark humor, kind of black comedy with his music, and a lot of political satire, you know, making fun of the political powers that be. Yeah, I was listening to a few songs when getting ready for this, and one of them was about basically everybody getting blown up by the bomb. It was kind of dark humor, but it was kind of making fun of like our current situation back in the 50s, 60s, where everybody was scared to get a nuclear bomb. So a couple of his songs to note. First off is Lobachevsky in 1953. Basically says how to be successful as a mathematician. You want to make it in mathematics, then plagiarize, steal other people's work. That's the way to make it. Like, and it's the whole song about how a person learned that that's the best way. That's how come he's been really successful in mathematics, is because just steals everybody else's work. Poisoning pigeons in the dark. The park. This is another black comedy one, but it actually is about a real thing that happened where they were using, I think it was strychnine. It was actually what they were using to poison the pigeons, but he talks about in a song using like cyanide and strychnine to poison the pigeons. Everyone was putting out little pellets of it to kill the pigeons at the park. The Elements song. So a lot of people, if you've heard of Tom Lehrer music before, it's actually because you've heard the Elements in maybe science class. He actually sang through the entire periodic table of elements to the tune of the Major General song from Gilbert and Sullivan's Pirates of Penzance. One of my favorite musicals, actually, which I thought was kind of fun. And it's a song that's all about speed, so he's singing through pretty quickly. It's impressive to have him do all the different scientific names for the different elements and do them very quickly. I did post in my YouTube playlist the song New Math, which is from 1965, and it's a satirical look at the change, current in 1965, change in the way math was being taught. They were trying to get more abstract thought into mathematics teaching, kind of bring some of the stuff from the higher levels down into the grade levels. It was actually a largely unsuccessful change or push. A lot of what they did, there was a big pushback from teachers and parents saying that it was stuff that the students wouldn't really need in the future, or really just hard to cover all the necessary material because they were doing that. The thing I find ironic, if you watch the video, the way he shows the new math, he shows basically subtraction problem. He does some carrying and borrowing and stuff, and it all actually looks really normal to me and to most students I work with, because it's a change that happened in the 60s. And so some of those things, elements of that change actually have stuck, and we've actually learned, or we've been using that technique. So now, 60 years later, the stuff that he was talking about is kind of being new and weird and different is actually kind of normal to us, versus the method he learned, or the people, of his time were learning. He does get into the working on like a different base, which is kind of crazy, base 8, and that was kind of more the new math part, is the working in odd base sets, not, with base 10 number system and stuff. So you can see there is kind of some interesting aspects there. I always find this pretty poignant even nowadays, because nowadays we have people talk about the Common Core and all that kind of stuff, and it comes down again to trying to teach mathematics in a little bit different way and all the pushback that happens. So this new math video is actually kind of still really current to our time frame, even though it's 60 years old. Some other mathy music. So there are lots of musicians that have written songs featuring mathematics. Some examples: Kate Bush wrote the song "Pi," where she actually recites the digits of pi. Modest Mouse has the song "Never Ending Math Equation." Radiohead has 2 plus 2 equals 5. The White Stripes have a song called "Dark Math." Ace of Base made a song about the golden ratio, and there's more. So there's lots of famous and a lot less famous people. There's mathematicians who have written their own music, so you can look at that too. But yeah, there's lots of different songs that deal with that. It's pretty common. Okay, the second type of intersection between math and poetry is poems that aren't necessarily about math. They're not like solving a math problem or about a specific math topic, but they use mathematical imagery. And one good example of that is actually the poet Emily Dickinson. So she wrote lots of poetry. Mostly of it's not titled, so you won't see titles on her poems most of the time. But she did study mathematics in school, and she used a lot of mathematical terminology in her poetry. And that wasn't necessarily about math. Like she wasn't solving math problems like the Lilavati or Archimedes' cattle problem. But she did use these as terms that were something she thought would be kind of ubiquitous. Most people of her day and age would kind of know what these terms were talking about. So here's the one, a lot of people just call this, "We shall find the cube of the rainbow," because that's the first line. So we shall find the cube of the rainbow, of that there is no doubt, but the arc of a lover's conjecture eludes the finding out. So a few different math terms in here. First off, we have this cube. So back in the day when Emily was writing, one of the big things you learned in geometry classes were what are called constructions. And they'd give you basically a straight edge, unmarked ruler, so a straight edge, a compass, that you could use for drawing like circles. Or you put your pencil on there and it's got a point on the other end. You can like turn it and draw sort of circles. And you would try and like build things. One of the things that was famously difficult to do is find the cube of something, which you should know the cube. Remember, a cube is, product times itself 3 times. So you get a cube when you take, x times x cube. So finding the cube of something, trying to take a length and like cube it and get, itself times itself 3 times. That was very hard to do with these constructions methods they were learning. So finding the cube of the rainbow would be something very difficult to do. There is no doubt. Arc, so she mentions the word arc. So arc in mathematics is actually the segment, a piece of a curve. So arc is a segment of a curve. And then conjecture. I mentioned conjecture previously. Conjecture is when someone makes some kind of claim in mathematics that's not yet proven. So that when they said, Fermat said that a to the n plus b to the n equals c to the n has no, whole number answers for values of n bigger than 2. That was a conjecture. So conjecture is a unproven statement. And so what she's actually doing here, she's not actually, trying to cube something or find the arc or, solve a conjecture or anything like that. But she is mentioning terms, things like the cube that's hard to do, finding the length of a segment of a curve can be difficult. Conjecture is something where, you haven't figured it out yet. And she's writing about how understanding love and a lover's, ideas and stuff like that is really difficult. So she's using math terminology to talk about difficulty and also to make something, okay, I'm trying to figure this out, and that's hard to do, which I think a lot of us can relate to with mathematics, right? Sometimes we get some hard math problems where we struggle with those. And so she's using that sense of mathematics, even though she's not solving a problem or talking about mathematics specifically. Her poem's about love, but she's using these mathematical terms in there. Another one is Barbie Says Math is Hard by Kyoko Mori. It came out in 1994. So as a boy, I'd still have asked why Jack must spend exactly $2 at the corner store. Give him a coin purse is as good an answer as 5 apples and 2 oranges. Also, would he bake the apples into pies or cobblers? Save the orange peel in glass jars to spice up his tea or cake? If his father paints their house with Mr. Jones, which man will take the peaks and why? Would the raspberry beetles swarm over wet paint? Why is Mr. Jones slower than his neighbor? If x equals y, is it like putting apples into coleslaw the way a tomato is really a fruit? None of my dolls talked or grew hair. In third grade, Satsuki and I traded our Barbie's limbs so mine could flex her biceps while hers sat cross-legged, raising one stiff arm like a weapon. If Satsuki has daughters, she might remember the grasshoppers we caught, how we cupped two hands together into crooked globes to hear them rattling inside like a small motor. She would tell her daughters, yes, math was hard, but not because we were girls. So a couple things. Why does she talk about math is hard in Barbie? So this poem came out a little bit as a response to the Teen Talk Barbie. So it was a Barbie where you press a button and it would say different phrases. And one of the stock phrases it said was, math is hard. And created a pretty big backlash. A lot of people saying math is not hard for girls specifically, but this makes it look like that's what Barbie's trying to say, and just kind of pushing on this stereotype that women have a harder time in mathematics. And so this poem is a response to that. You know, that math being difficult is not about being a boy or a girl. She does mention some math things, so you can see like as a boy she'd ask why Jack must spend exactly $2 at the store. So that's the whole math problem. So these are story problems where your teacher says, okay, well, they have this much money to spend, have to spend it exactly. What could they buy? So says, well, just give them a coin purse and let them spend as much, the coin purse, right? You don't have to like get, a specific amount. It's silly. What's more important is what is he going to do with the fruit, right? That's a more important question, she says. She talks about his father, Mr. Jones, painting the roof, or paint the house. So, there's a lot of story problems where they say, okay, if one person can do it this speed, another person can do it this speed, how fast do they get it done together? So it's a rate problem. She's saying, well, more important, who's going to take the hard parts? Are they going to have bugs in the paint? Like, why is one faster than the other? If x equals y, if you're solving algebra equations with letters, what's that really mean? And then she talks about her Barbies and stuff and how they played with Barbies, but, it wasn't about being girls and not being able to do math, and this is just silly that they did this with this math Barbie. So again, the poem uses mathematical terminology, uses these phrases, and talks about stories and stuff. But it's about being a girl. It's about stereotypes. It's about the difference between math expectations and story problems, and like the problems actually matter in real life. Alright, this is Which Girl Am I by Joanne Growney, 2014. The girl who's not forced to divide into the good girl and the real one is a lucky one. I was 11 when I felt a crack begin. In time I fully split. Two minds took on two heads, two faces, two cuts of hair. Mock feelings served as well as true ones. I told myself, but buried parts still surface like cicadas in their year. Long division is difficult and plagued with remainders. A girl with two heads is like a bird with one wing. So again, this poem's not about math. We're not solving a math problem, but she is mentioning things like long division and remainders, trying to split into two. But of course, dividing. So she's talking about division, splitting, and this all kind of stuff. But the poem definitely is more about, when you feel like you're pressured into acting different ways for different sets of people. So, Joanne Growney, just more interesting, is a math teacher. Was a math teacher. She's retired now. She taught for over 28 years. She actually developed a pretty strong interest in poetry during that time. So she went and completed a degree in creative writing, and she's actually written several books of mathematical poetry, so poems that connect with mathematics. And she has a whole blog and website, and she really works in looking for poetry that is connected between math and poetry. This is The Limitations of Proof by Ben Orlin. I cannot prove I love you. I don't mean to be rude, but I cannot prove I love you, not with any certitude. There's no good proof I love you, and I know that sounds phlegmatic. It's not that I don't love you, just the love is axiomatic. And a thought bubble, conversation here. I thought you said proof is the only measure of certain fact. Sure, but what does certain fact have to do with anything? So this guy, Ben Orlin, actually has written several books about math, and he's famous for his first book, which is math with bad drawings. And so it's pretty humorous. He's drawing your little stick figure and stuff where they're not, super wonderful drawings, but they're fun and they're well made, cartoonish. And he has a book called Math for English Majors. Yeah, this is from Limitations of Proof. And of course, you can't really prove love, right? Because mathematics, you have to state all these logical arguments, love beyond proof. And again, it's not so much about math, it's about, love and relationships, not complex, and they don't just have simple proofs. So we're using mathematical terms, but we're really talking about something else. Math isn't really the focus, but it's in the poem, it's in the poetry. Okay, our last section. So these are poems not necessarily about mathematics at all. They don't necessarily, talk about mathematics, but they have strong structure, and this structure could definitely be considered mathematical. There are going to be ways where this is connected to mathematics because of just the structure, the design of the poem. So there are many forms of poems that exhibit a strict structure requiring a certain number of words, a certain number of syllables, or even a specific arrangement of the words. We'll cover a few different ones. The first one is a square poem. So this was written in 1597. This poem was written by Henry Locke in honor of the Queen Elizabeth I. Now, if you count, the lines down the side here, and then you count the number of words in any of these lines, you see that there are 10 lines and there are 10 words. And that'd be, already a square, and it would be mathematical, but it actually has a lot more structure than that. So the poem is actually designed so that, yes, you can read a 10 by 10 poem that is a square because it's 10 words per line times 10 lines. But it actually has lots of different things. Like you can actually read it as a St. George cross, which is a plus. So if you actually read down this way and then out, and then I believe it's down this way and then down, you can actually read it like this. So there's a St. George plus, cross plus. There's also the St. Andrew's cross where you can actually read it on the diagonals. So there's the diagonals that you would read down this way. I forget what the order is, but so there's another poem you can read that way. For the two pillars where you can actually just read the two lines on this side, and that makes a poem. The idea was Henry Locke was thinking, well, Queen Elizabeth has lots of different virtues. She's a great queen, so I'm going to write a poem that can be read in lots of different ways to show off all her different virtues, or show off so that she has so many different virtues. So it's funny because now I looked this up, and for a long time I didn't realize that there's all different ways to read this. I thought it was just, it's 10 by 10, but it's not that simple. There's actually a lot more going on there. And it's actually pretty complex, all the different things he's built into this. And again, this is a grid showing you how it works, but when you present the poem, it looks like this, and then you read it and go, oh, but you can do this, 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 and this, and there's all these other poems hidden inside. Another square poem was written by the one author of Alice in Wonderland, so Lewis Carroll. He invented his own version of a square poem. This one is cool because it reads the same if you go vertically as if you go horizontally. So you can either read, I often wondered when I cursed, or I can read, I often wondered when I cursed. And you get the same poem either way. So you could read, like, I often wondered when I cursed, often feared where I would be, wondered where she'd yield her love, when I yield, so will she. I would her will be pitied, cursed be love, she pitied me. So kind of a crazy thing, it works either direction. What ends up happening is to write this poem, he actually has a lot of words where, since it's in one spot, it has to be another spot. So a lot of the words are forced. Once you pick a word often here, you have to have often there. If you pick the word wondered here, you have to have wondered there. You have her here, you have to have her there. So that is all forced. Really complex thing to write. I've seen people talk about trying to write these, and I haven't really tried it myself, but just to show that, like, I've seen him talk about how difficult it is because you really have to think ahead about, well, if I put this word here, then I'm stuck with this word there. And especially when you get to this where he's got like a 6x6, the bigger it gets, the harder it gets. Now, for our homework, for the quizzes, for the exams, we'll keep it simple. I'm not going to expect you to be like, oh yeah, this is a square poem because it can be written read a whole bunch of different ways or like multiple different ways. We'll consider a square poem if it has the same number of lines as it does number of words per line. So if it's 6 words for 6 lines, or 4 words for 4 lines, 10 words for 10 lines, that's what we consider a square poem. So when you're doing the homework and stuff, if you're looking at a square poem, it's got 3 lines and each one has 3 words, that's a square poem. So that's one type of structure, square poems. Next one is haikus. So haiku, poetry originated in Japan, consists of 3 lines with 17 syllables. In Japanese, that would actually be considered on, which are a little different than syllables, but in English, we just do it with syllables. Typically, the first line has 5 syllables, the second one has 7 syllables, and the third has 5 syllables. Traditional haikus usually include what's called a kireji. It's a cutting word, so basically kind of a split in the poem. It could be after the first line, after the second line, or it could be at the end of the poem. Sometimes that kireji is at the end to kind of give a more dramatic like finish to the poem. And then a kigo, which is a seasonal reference. So it could be kind of reference to the time of year, that kind of thing. So again, this is built out of Japanese language, so it doesn't quite translate perfectly to English. And actually, this whole count of 5 syllables, 7 syllables, 5 syllables, which is what we really kind of are going to latch onto for this class, and what you learn in like grade school and stuff, is probably not the most important part of the poems. Like that, having that seasonal reference is the one thing that they always have to have. The kireji, the cutting word, can be dropped sometimes. The 575 can be dropped sometimes, but there's a certain style to these that really kind of lets you know if it's a haiku. And there have been people that have experimented and kind of gotten a little off, a little different from that 575. But for our class, for our purposes, we'll say 575. So 5 syllables, 7 syllables, 5 syllables. So here's a couple haikus. This one I thought was fun because it's a haiku explaining what a haiku is. So first, 5 syllables. Second, 7 syllables. Third, 5 syllables. And so you count as 575. So it's got more syllables in the middle than it does on the other two. But yeah, so it's a haiku with syllables. This was actually a math haiku. So 2 lines side by side. Never meeting is their fate. Same slopes are their curse. So again, 1, 2, 3, 4, 5 syllables. Same slopes, 1, 2, 3, 4, 5 in the middle. 1, 2, 3, 4, 5, 6, 7. 7 syllables. So 5, 7, 5. So this is talking about parallel lines, how they never cross. This is a haiku by Tao Wang. So once Euler looked out at 7 bridges to cross. Can't be done, he said. And this is actually about a famous math problem. It's called the Königsberg Bridge problem. So basically there was a river, a stream with a little island that had some bridges on it. And then there's like a little inlet over here with some more bridges. And he wanted to know if you could cross all the bridges exactly once, never cross the same bridge over again. So like I can't go back over a bridge once I've crossed it. And can do that if you can transverse this area and cross all these bridges once. And actually, a lot of people wanted to know that. It's kind of a common thing. Like, hey, there's all these bridges right here. Is it possible? Can I just walk and cross? Like, can I start at a certain spot and like walk across all the bridges and not ever cross one? Then I missed this bridge. So, well, he proved out that it can't be done. He actually had to like really dive into this problem to figure it out. And he actually started a whole field of mathematics called graph theory, where they look at like how things are connected. It's an entire field of mathematics. I've been to math conferences where they have a whole segment dedicated to graph theory because it's a branch of mathematics now. You don't usually study it until you get to higher level mathematics, but it's a really important branch of mathematics. And so he started that by solving just this one problem. From Reality's Tides by Stan Sand, Golden Ratio and Fibonacci Sequence govern nature's shapes. So I talked about last time how the Golden Ratio and Fibonacci show up, and it's a poem dedicated to that. The Fib. The Fib is actually a more recent creation. It is a poem consisting of 6 lines, where each line has a syllable count equal to the corresponding Fibonacci number. So it's going to be 1, 1, 2, 3, 5, 8. It was first created by Greg Pincus in 2006. So this is not that old for poetry terms. In fact, this is the first Fib that Greg Pincus wrote that really kind of made the style famous. So the Fib by Greg Pincus: one small, precise, poetic, spiraling mixture. Math plus poetry yields the Fib. As you can see, he's doing one small, precise, so 2 syllables, poetic, 3 syllables, spiraling mixture, 5 syllables, and math plus poetry yields the Fib is 8 syllables. So it's a syllable count where you start off small and you're getting bigger over time. Now, some people do this with more than just 6. You'll see some where they have 13 or 20. They'll have the next numbers that come with the sequence. So instead of 6 lines, they have 7, 8, 9 lines. Some people do short fibs where they only do like 4 or 5. So the number 6 lines is not necessarily strict or anything with fibs. You'll see all kinds of lengths of fibs, but the idea is that each line should be based on the count of the Fibonacci sequence. Here's another one. This is one I thought was pretty cool. So, fib? No, no way, never I would never lie, unless it was a little fib. So, fib about fibbing. Taking this even to a higher level, this is a poem by Sherman Alexie, a pretty famous indigenous author. So he wrote a Fibonacci sequence poem where he climbs up the sequence and he actually climbs back down. So he's going to start with 1, 1, and then 2, 3, 5, 8, and go until he gets to like 55 syllables, and then he's going to count back down 34, 21, until he's back down to 1, 1. So he got it. All that autumn, I walked from the apartment shared with my sisters to that payphone on 3rd Avenue next to a sleazy gas station and down the block from the International House of Pancakes. I was working the night shift at a pizza joint, and you were away at college. You dated a series of inconsequential boys. Well, each boy meant little on his own, but their cumulative effect devastated my brain and balls. I wanted you to stop kissing relative strangers, so I called at midnight as often as I could afford to. If I talked to you that late, I knew, or hoped, you couldn't rush into anybody's bed. But damn, I still recall the misery of hearing the ring, 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 ring of your unanswered phone. These days I'd text you to find you, but where's the delicious pain in that? God, I miss standing in the mosquito dark at this or that payphone. I wish that I could find one and call back all that I loved. So be ready to talk about fibs. Again, fibs, you should be able to identify that structure where you start off with shorter syllables, less syllables, and you get more syllables till the end. And we'll just do it that way. We're not going to go with the full out and back. We'll keep it simple. Okay, sestina. So far I've been doing like syllable counts and word counts. Sestina, we're going to get into arrangements of words. It's kind of a crazy idea. So this is a poem consisting of 6 stanzas, which is a set of lines, kind of paragraph for poetry. Each one has 6 lines. Normally, it's followed by a 3-line envoy or a little short stanza that basically kind of comments on the poems and reiterates some things. So you'll have like 6 stanzas plus a little envoy. The words at the end of each of these lines of the first stanza are rotated and used to end subsequent stanzas, attributed to Arnaud Daniel. So he was a poet from basically a south of France, but it was a non-French speaking area. They've had a different language and stuff. And, older, 12th century, things were a little broken up, not so centralized government languages and stuff. But he was a poet, troubadour. And this is his idea was he was kind of first person. So these weren't originally written in English. They actually first started getting published in English in like the 1500s, and they did have kind of a resurgence in the 20th century, so the 1900s. Okay, so this is a sestina by Elizabeth Bishop in English. So, September rain falls on the house. In the failing light, the old grandmother sits in the kitchen with the child beside the little marble stove, reading the jokes from the almanac, laughing and talking to hide her tears. She thinks that her equinoctial tears and the rain that beats on the roof of the house were both foretold by the almanac, but only known to a grandmother. The iron kettle sings on the stove. She cuts some bread and says to the child, "It's time for tea now," but the child is watching the tea kettle's small, hard tears dance like mad on the hot, black stove. The way the rain must dance on the house. Tidying up, the old grandmother hangs up the clever almanac on its string. Bird-like, the almanac hovers half open above the child, hovers above the old grandmother and her teacup full of dark brown tears. She shivers and says she thinks the house feels chilly and puts more wood in the stove. It was to be, says the marble stove. I know what I know, says the almanac. With crayons the child draws a rigid house and a winding pathway. Then the child puts in a man with buttons like tears and shows it proudly to the grandmother. But secretly, while the grandmother busies herself around the stove, the little moons fall down like tears from between the pages of the almanac into the flower bed. The child is carefully placed in the front of the house. Time to plant tears, says the almanac. The grandmother sings the marvelous stove, and the child draws another inscrutable house. So the big thing here is not the number of syllables or not the number of words, but the big thing is the words at the end of the sentences. You'll notice the same 6 words keep reappearing, right? We have house, grandmother, child, stove, almanac, and tears. And here we go, tears, house, almanac, grandmother, stove, child. It's the same 6 words, but they're always in a different order. You start with house, then start with tears, child, almanac, stove, grandmother. Every word is going to be in that first place once. Every word's going to be in the second place first once. Except for this last phrase. This is the envoy. You'll see we have all 6 words in this envoy. So there's 3 sets of 2. And this one, you don't get to cover everything. This is kind of repeating almanac here and these other ones. So really, if you just look at the first 6 stanzas, these are the main part of it where you're looking at the reiteration. Now, how does this work? How do they, figure out how to order these? Well, they start off with, the 6 words, house, grandmother, child, stove, almanac, tears. And what they did is they said, okay, the next order, the next one, we're going to start with the 6th word, and we're going to go to the first word, and then we're going to spiral until we used all the words. So we're going to start with the 6th word. So we start with tears, go to house, and then from house we go to almanac. From almanac we go to grandmother, and from grandmother we go to stove, and from stove to child. So the next order is tears, house, almanac, grandmother, stove, child. And if you do that, every time you do that, you'll get the next stanza's order. So like here, we'd start with child, and then go to tears, and there's child and tears, because we do that same, going around. And so you can do that every time. So basically, the sestina, every stanza, you start at the bottom, go to the top and go kind of spiral through until you used up all the words, and that gives you the next order. So like this one starts with 3, 6, 4, 1, so 3, 6, 4, 1. This one would start with 5, 3, 2, 6, 5, 3, 2, 6. This one, 4, 5, 1, 3, 4, 5, 1, 3. 2, 4, 6, 5, 2, 4, 6, 5. So that's how they're getting this. So the order of the stanzas, you start with the last word, and you spiral to the middle, and it gives you the order for the next stanza. So it's a pattern that they do the same method every single time, and it gets you through all 6 words, and you end up with every word in each place once, right? So the 6th word is, here's the first, second, 4th, 5th, and then 3rd spot, and it was already in the 6th spot to start with, so it's covered all the spots. Or here you have the word number 1, and the number words here, and then it's here, here, and back up here, and then down here. And so it kind of spirals, it goes through all these different spots. So that's how a sestina works. The sestina is all about following a pattern and getting all these words rearranged so that I end up in the correct locations. Now, mathematicians saw this and said, hey, this would be cool if we could kind of generalize this. Could we do this with any number of words? We did it with 6 here, where we had 6 stanzas with 6 lines, and we rearranged those 6 words. Could we do it with any number of lines? Could you do it with 12? Could you do it with 5? It doesn't always work. And so that's what they studied. Mathematicians looked and they generalized this to n lines. We call it a quinina after the poet Raymond Queneau, because he worked with some mathematicians to do this. He's one of the first people to really get this idea of a generalized sestina. For the structure of the work, the spiral technique must place each word in each location exactly once. You still have to follow that same spiral technique, and everything has to end up in one spot, within the so many tries. You can't go back to the beginning too soon. You can't miss a word or have a word never get to a certain spot. So let's show simple examples, see if these work. Well, n equals 1 is really easy because you only have 1 line, 1 stanza. It's done. It works. Not too hard. 2 is also pretty easy because you do your spiral, you start with the bottom and go to the top, and so I'm going to do trigonometry, which would be trigonometry. So yeah, 1 and 2, pretty trivial, not that big a deal. Let's look at 3. So 3, I start with, I have inequality, can have numbers multiply but later divide. Well, now I'm going to have to start with the bottom, divide, go up to equality, and then down to multiply. So I'm going to have to do divide, equality, multiply, which I do divide, equality, multiply. And so it does work. If I keep going, I try it again. I do multiply, divide, equality, so multiply, divide, equality, and you notice I have multiply in the middle, the bottom, and the top. I have divide on the bottom, the top, the middle, equality at the top, the middle, the bottom. Everything ended up in one spot exactly one time. It did work, so this does work for 3. In fact, in 1969, Munich proved that you can only have an n-ina, so something with that will have this setup like this or work like this, if 2n plus 1 is prime. So if I take like the number of lines, multiply by 2 and add 1, if that's a prime number, remember a prime number only divides by 1 in itself, then you might have a quinina, or quinina and nina. However, that actually isn't enough to prove that it works. So we'll see a counterexample here in a little bit. But that's a requirement. So first off, I can look at like, okay, 1. Well, if I did 2 times 1 plus 1, well, 2 times 1 is 2, plus 1 gives me 3, and 3 is prime. So, and then we knew it's going to have to be prime because we already saw that 1 works. But yeah, 1 does work, and yeah, 1 is, give us a prime number because 2 times 1 plus 1 is 3. Now, it's not about whether 1's prime, it's about whether 2 times 1 plus 1 is prime. So like here, say 2 is prime, but we want to check actually if 2 times 2 plus 1, if that's prime. 2 times 2 is 4, plus 1 is 5, and yes, 5 is prime. So this one checks out as well. This is also prime. And that makes sense because we already saw that works. So we expect this one to work. Let's try it. 2 times 3 plus 1. Well, 2 times 3 is 6, plus 1 gives me 7. And again, that is prime. So yeah, anytime that it works, anytime this works, this will be true. So if you find one where it's not prime, if you do 2 times n plus 1 and you get a non-prime, then you know it's not going to work. So let's actually do it for another couple. We don't know if they work yet. Let's try 4. So we're going to do 2 times 4 plus 1 and see if it works. Well, 2 times 4 is 8, plus 1 is 9, and 9 is actually not prime. It's odd, but it's not prime, and usually primes are odd, so that's kind of confusing. Remember that 3 times 3 gives you 9. So the factors of 9 are 1, 3, and 9. It's got too many factors. Prime means the only factors, the only things that go into it are 1 in itself. So this is not prime. So actually this one won't work. There's no quinina. I can show you how come. Let's actually do that real quick. So the reason this doesn't work is if you start with your last words, rainbow, doubt, conjecture, out. I'm going to just do A, B, C, D because that's easier than having to write the words over again. If I do the quinina setup where I start with my spiral, I'm going to do D, A, C, B, and I write my next line. So I start with D, and then I do A, and then I do C, and then I do B. You notice that right away this failed because C is now in the same spot. It's not moving. In fact, if you keep trying this, you'll see that C never moves. So this one doesn't work because when you try and do your spiral, you always end up with C in the same spot, and it doesn't cycle through. So I do end up with B moving, and I end up with D, but then I end up with C, and then A. And again, C is just stay in the same spot each time. So this is why this is not working. And if you keep going, A, B, C, D, you actually get back to the starting point before you've even run through all the different possible combinations, right? We haven't put C in all its different locations. A, B, and D never end in the middle, so it's not working. C doesn't move. And there's lots of reasons why these won't work. This is one reason. Sometimes you'll have a letter that doesn't move. Sometimes you'll cycle through and get back to the start before you've gone through and put everything in all the locations. Like here, A has not gone to the third spot yet, so that's one problem. So yeah, you don't have to show this, right? This is one way to check it. You can just do the spiral and see if you end up missing locations. But another valid way to check it is if you get a non-prime, it's not going to work, guaranteed. Let's try 5. So let's see if 5 could work. So first off, if 5 is going to work, we have to be able to take 2 times 5 plus 1 and get a prime. Well, 2 times 5 is 10 plus 1 is 11. It is prime. Now remember, this is not a guarantee it works. That's actually not enough to say it works. It's just enough to say it could work. If it's not prime, you can say it's not going to. Actually, we knew this was going to fail. It could work. Let's check it. To check it, we're going to do that same thing. I'm going to do A, B, C, D, E. Now I got 5 letters because I've got 5 lines. And we're going to see if the spiral works. I'm going to start with the bottom. I'm going to spiral up to A, from A to D, from D to B, from B to C. So my new line would be E, A, D, B, C. So that's just the order we went. So E, A, D, B, C. Next thing is C, E, B, A, D. So I have C, E, B, A, D. And so far, notice I haven't repeated anything, right? Nothing's ended up in the same spot. They're always moving around. So I'm going to keep going. So I'm going to do D, to C, C to A to E, E to B. So I have D, C, A, E, B. And still so good so far, right? Everything's moving around, always getting a different letter. So I'm going to try keep going. B to D, D to E, E to C, C to A. So I get B, D, E, C, A. I've actually got 1, 2, 3, 4, 5. 5 stanzas is what I needed with 5 lines. And you can see that every letter is always in a different location. You know, A is up here, then it's down here, then it's further down, in the middle, and then the bottom. Everything's moving every time. So this works. It wasn't enough just to say it was prime. We actually had to check it, because once you know it's prime, it's possible it works. If it's not prime, you can say, well, guaranteed to fail. But if it's prime, you actually have to look and see, does the spiraling technique work? And the spiraling technique works for n equals 5. You could actually take this and write n-ina, a 5-ina, using 5 lines, where you just take those 5 words and cycle. It would work. I got one more question for you, and then we're done. Does 8 or 9 work? Let's see if 8 or 9 works. So first off, to do 8, so n equals 8. First off, we're going to do that, n times 2 times n plus 1. So we'll say 2 times 8 plus 1. Well, 2 times 8 is 16 plus 1 is 17. So it could work, right? This actually so far says, might work. It is prime. 17 is prime. We've got to check it. So let's try it. Let's do this. So I'm going to do A, B, C, D, E, F, G. So 1, 2, 3, 4, 5, 6, 7, H, H. So 8. So I got 8 letters of the alphabet. If I do my circle, so I start from H and go to A to G, G to B, B to F, F to C, C to D, or E and E to D. I end up with H, A, G, B, F, C, E, D. So far it's not looking bad. Everything's moved, so I keep going. And I'm going to do D to H, H to E, E to A to C, C to G, G to F, F to B. I do that same cycle. Let's see if it works again. So I start with D, I do H, I do E, I do A, I do C, I do G, and then I do F, and then I do B. And so far everything's different, I believe. Keep going. You're like, do I have to do this all the time? Well, I'll try to be nice and not give you huge numbers for the test, or I'll give you numbers where it obviously fails, like if it's not prime. But yeah, let's try this. So I got B, D, F, H, G, E, C, A. And okay, how many do I have so far? No repeats, I don't think. Looking good. Let's keep going. I'm just going to jump. I'm going to draw the lines anymore just to go faster. So A, B, C, D, E, F, G, H. And we go, wait a second. That's the first one again, right? We just got a repeat. This is a repeat. And we're only 1, 2, 3, 4, 5 stanzas. We didn't get through all 8 stanzas. So this one actually fails. So this is what I was talking about. Being prime here doesn't guarantee it works. It does require it to be prime before it can work. So if it's not prime, it won't work. But being prime doesn't guarantee it works. You can't just say, oh yeah, 17's prime. The 8-ina works. 8-ina actually fails. You can't do an 8-ina. Let's check 9, and then we'll be done. So say n is 9. First off, we're going to do 2 times 9 plus 1, see if that works. So I get 2 times 9 is 18, plus 1 is actually 19. This one is prime. And I'll just tell you, instead of having to write this out and sit here and listen to it over and over again, if you did it with the letters, the cycle does work. Again, on the test, I'm not going to give you like an n equals 9, make you have to sit there and draw the cycle 9 times. I'd probably give you something smaller. And again, if it's not prime, if it's like number 4, where it was not prime, in that case, we knew right away it wasn't going to work. We really didn't need to do this test because we saw that 3 by 3 was 9, not prime. We knew it was going to fail. I just showed you how it failed. That's the one I'd probably give you something like that, where if you multiply it times 2 plus 1, you get a non-prime, then you know it fails. Or I'll give you something fairly small, so it's easy to run the cycles. Something like 5, not like 9. 9's kind of a long time. So the cycle does work though for 9. You can do it. And there's actually, as far as we know, there's probably infinitely many of these. We're actually not sure. That's still an open problem. We don't know for sure how many of them there are. People have still been kind of working on this, and it's still an interesting problem for mathematicians. But basically inspired by poetry, by Sistina, started 1,200 years ago. So mathematicians are still looking at these and trying to understand it better. Okay, so hopefully the fact that you thought it was pretty interesting learning about how math and poetry can intersect. That is our last section to cover. All you have left is that 4th unit exam, which is just going to cover all this math and the arts we've been studying. So make sure you're setting up your appointment to get that taken. If you're in my online class, make sure you're getting ready to get that exam taken before the end of the semester. Good luck.